So now, in case that you want to use the formula to find the first one will be equal to the mass of the S times mass of the satellite, which is ms, times universal gravitational constant, and the distance between the center of the satellite and center of the S is x squared. Right? So suppose that this is the first equation and this is the second equation. So again, the force of attraction between the satellites and the sun, ms times mass of the satellite. So for this case now, it's better for if you use this notation, st, mst. So then this is st to differentiate the notation for the mass of the sun and mass of the satellite. Okay? So then times 30 universal gravitational constant. The distance from the sun to the center of the satellite is r minus x. So this will be r minus x squared. So this will be the third equation. Right? Beautiful. Physics is beautiful. We got the fifth state. The fifth state now, we say that substitute equation 2 and the equation 3 into equation 1. So into this equation, where the gravitational potential is 0. So if you do that substitution, you find that the mass of the S, mass of the satellite, times gravitational constant, then you have distance x, we are looking for that x, and then you have mass of the sun, mass of the satellite, gravitational potential or universal gravitational potential, radius times x or minus x squared. So mass of the satellite and mass of the satellite cancel, universal gravitational constant, universal gravitational constant cancel, and then we have to remain with some few physical quantity. You see how gravitational or the concept of the satellite is very interesting? Yes, it's beautiful, interesting. So then, if that's the case, we remain now with the mass of the S, which have been given as numerator, then of 40, square of the distance between the center of the satellite and the center of the S. Then this is equal to the mass of the sun over radius or distance from the center of the S to the center of the sun square. So we know we have been given this constant, we'll be given this constant, we'll be given this constant. What are we looking for is x. So we have to go for the sixth step before the number of steps on solving this problem. The sixth step, we say that we have to make x the subject. So you have to make x in this equation the subject. So how will we achieve that? First of all, we have to reciprocate equation what? Equation 5 or equation 4, right? Equation 4. Reciprocate equation 4. So if you reciprocate equation 4, we have x squared over mass of the S is equal to the distance from the S to the sun square of 40 mass of the sun. So next thing you can expand. To make it the subject, you can expand and then make the subject, or you can do the computation the way it is. I think the simplest way, no need for you to make the x the subject, is just you have to make the computations, or you can even find the square root and so forth. So we are still proceeding, okay, to make x the subject. So then we say that if for this case we have to cross multiplication, and then when we cross multiplication, we have x squared, mass of the sun, is equal to mass of the S. Then we have what? Distance from the S to the sun squared. Right? And then we have to divide with distance from the sun square minus this one, and then divided by distance from the sun to the S this guy square, then divided by mass of the sun, divided by mass of the sun, so this and this will cancel, and this one and these items will cancel, so it remains with x, then radius, this one square is equal to what? Mass of the s over mass of the sun. So you have to find the square root of both sides. We have x over distance from the s to the sun, okay, x, then this is equal to the square root of mass of the s over mass of the sun, right? So if this is the case, so we are still looking for RT for the value of this one, so we can have x is equal to what? So we can cross multiplication, so this is equal to r minus x, and then we have what is square root of mass of the s, mass of the sun, right? So then, if we keep on simplifying the expression, we find that x is equal to r square root of mass of the s over mass of the sun, right? And then minus x over square root, or times the square root of mass of the s over mass of the sun, right? So then we have x plus x, and then this is square root of mass of the s, mass of the sun, is equal to distance from the s to the sun, and then square root of mass of the s over mass of the sun. So x is common, right? So then we have x1 plus square root of what? Mass of the s, mass of the sun, is equal to radius, square root of what? Mass of the s, mass of the sun. So then we are looking for x. X is equal to what? Distance from the s to the sun, mass of the s over mass of the sun, divided by 1 plus square root mass of the s, mass of the sun. So x is equal to what? R it is 1.5 exponent 11 meter, and then square root mass of the s, it is 6 exponent 24, and mass of the sun is 2 exponent 30, and then divided by 1 plus square root of what? 6 exponent 24 over 2 exponent 30, and we'll get x. So by using your scientific calculator, the value of x, which will be the distance from the s's surface, the value of x is 2.259 exponent 8 meter. So x is equal to 2.59 exponent 8 meter. So this is the distance where the gravitational force is 2.59 exponent 8 meter. So therefore, we conclude that the distance is 2.59 exponent 8 meter, exponent 8 meter. From there, you have to say from where? From the s's surface. From the s's surface, because that's how we let. In case you'll be asked that from the sun surface, so in case that, for example, that not before, in case the distance is from the sun surface, so we say that we'll find by taking r minus x, the distance from the center of the s to the sun minus the x. The x is this one. So for that case, it will be 1.5 exponent 11 minus 2.59 exponent 8. Then we get a distance where the gravitational force is 0. Okay? Okay, in case you have any questions or you didn't understand at any point, please don't hesitate yourself to ask in the comment section. So I believe you enjoy that question, and you have understood it well. Let me give you now the next example relating to what I've taught you. So this is example 7, 8, this is the example 9, and this is homework 7. So this is homework 7. It's a conceptual question. And then I took it from the reference book where I took this question is Nalcon. Okay. Nalcon, the out of the book. The book is called Physics or Advanced Physics. So the book is Advanced Physics, but we used to name it according to the author. Advanced Physics by Nalcon and Packard. The page where you find this question, page 191. As I told you in the reference book, the reference books that I'll be using in teaching you concept of gravitation. Okay, so the question was stating like this: the mass of the S is 81 times the mass of the moon, or 81 times of the moon. Let me copy the way it has been written there, of the moon. And the distance from the center of the S. From the center of the S to that of the moon, is about 4 exponent 5 kilometer. Calculate the distance from the center of the S. Calculate the distance from the center of the S. From the center of the S. Of the S, where the resultant gravitation, where the resultant gravitational force becomes 0. Becomes zero when stress gravity is launched from the S to the moon. Launched from the S to the moon. The spacecraft is launched from the S to the moon. So that's a question. So let me read the question. The mass of the S is 81 times of the moon. Remember these questions I took from the Advanced Physics books by Nelson and Parker, page 191. The mass of the S is 81 times of the moon, and the distance from the center of the S to that of the moon is about 4 exponent 5 kilometers. Calculate the distance from the center of the S where the resultant gravitational force becomes 0. So this is full stop. So this is capital. When spacecraft is launched from the S to the moon. So that's the question. Try it. Enjoy it. Dance with it. Sing that chorus. Compose a bass on it. Test yourself if you understand what I've been teaching you. Remember that there are question and answers books, that is review books, and even reference textbooks. They contain a lot of questions of gravitational mechanics. So make sure that you go through them, solve the problem, enjoy the beautiness of what you've been solving for, and then you advance your understanding step to step. Okay, so let us go to problem 10. Say example 10, in this problem solving. Also, this is a conceptual question. Okay. The question states that an artificial satellite of mass 100 kilogram in a circular orbit. Circular orbit of 500 kilometer above the S's surface. Above the S's surface. If the radius of the S is 6.5 exponent 6 meter. After full stop. Find the following. Find command 1 Z acceleration. The acceleration due to gravity along the satellite orbit. Then Roman 2, find the centripetal. Find the centripetal acceleration. Centripetal acceleration. Acceleration. Find the centripetal acceleration of the satellite. That's why I told you that every question is meaningful, every question is important. I don't repeat questions in order to add the number of the questions that, oh, we have solved this number of questions. So read that question carefully. Remember all the concept of the artificial satellite that I've taught you. Remember also for part B or for the second part, remember the concept that I've taught you in circular motion. And then enjoy the beauty of the question. Okay? So the question states that an artificial satellite of mass 100 kilograms in circular orbit or 500 kilometers above the Earth's surface, if the radius of the Earth is 6.5 exponent 6 meters, find Roman 1, the acceleration due to the gravity along the satellite orbit, not along the Earth's surface. Be careful. Roman 2, the centripetal acceleration of the satellite, not centripetal force. Be careful. Because we experience to know, we've been singing a song, a chorus known as centripetal force. No, the questions ask you centripetal acceleration. And nothing new there. That's all about the world of physics. So you have to enjoy it. And you should be familiar on them. So if you're not familiar on them, join me, please, in a few minutes. I'll be trying my level best to relieve. It means that to reveal the secret to you. Okay? So if that's the case now, we say that we have to be careful. A satellite will be given the mass of the satellite, will be given the height from the Earth's surface, will be given the radius of the Earth, then you have to determine some other physical quantities. Right? That is very important. So you say the first step, so solution, first of all, let us solve that problem. So the first step, we say that let us consider data given. Okay? So the data given, we say that the big given what? The big given is number 1, mass of the satellite. Mass of the satellite, let's say ms. This is equal to what? 500 kilograms. Is it 500? 100 kilograms. Okay, 100 kilograms. Then the height h of the satellite from the Earth's surface is 500 kilometers. And then the radius of the S, and this we call TRE, this is equal to 6.5 exponent 6 meter. What's required? We are required to find acceleration due to gravity on the satellite orbit, not the one, the satellite orbit. This is required. Also, we have to find what the centripetal acceleration. interesting. Make sure you do this homework in case you find some difficulties on solving it. Please don't hesitate yourself to share your comments on the comment section of this video. And then some other students might come with a correct response, or even myself as your teacher. Thank you very much for giving me an opportunity to be a teacher of advanced physics. Okay? So, in order to navigate with that question, we say that the second step, we have to sketch the problem. Sketch the problem. So to sketch the problem, we say that we have the SC surface. The question does not talk about moon, talks about the S. So this is mass of the S. And then we have the circular orbit of the satellite. Circular orbit of the satellite. So that's the mass of the S. And then we say that here we have radius of the S. And then here we have the height. Height, h, above the satellite's orbit. So this we call the satellite orbit. It might be parking orbit, might be another orbit. So this we call the satellite orbit. And this what we call the Earth's surface. Earth's surface. Okay? So that the Earth's surface and that the satellite's orbit. So our intentions is to find the gravitational or acceleration due to the gravity along the satellite orbit. That's what we've been asked, not on the Earth's surface. You have to find acceleration gravity on the satellite's surface. So the steady state, we say that we have to recall the formula of what? Of Newton's universal gravitation. Universal gravitation. So the formula says that the force of attraction between the satellite and the S, mass of the S times universal gravitational constant, and then for that case we say that radius of the S plus the height above the S's surface, and this one square. So this will be our first question. So again, we have to carry on. Remember that the satellite we are discussing, before it has been fired vertically to its orbit by using a rocket, it was on the Earth's surface. So the first step, we say that consider a satellite on the Earth's surface. On the Earth's surface. So that the satellite is on the Earth's surface. So when you consider satellites on the Earth's surface, then you say that the weight of the satellite, that is mass of the satellite times acceleration gravity on the Earth's surface, because the satellite is still on the Earth's surface, has to be equal. It should be balanced to the mass of products of the mass of the Earth, mass of the satellite, universal gravitational constant, and then a radius of the S square. That is on the Earth's surface. So consider the satellites on the Earth's surface. So what do we mean? We mean that this is the Earth's surface, for instance. This is the center of the Earth. So we have mass of the Earth, and then the satellite is here. So we have ms. So the distance from the center, the satellite, the center of the Earth, this is what we call the RI. So understand it, because it might give you confusion. If that the case, the mass of the satellites and mass of the satellites will cancel, so acceleration gravity on the S's surface will be given by the mass of the S times gravitational or universal gravitational constant, then times radius of the S square, and this will be our second equation. The fifth step of solving this problem in part 1, because we are still solving part 1, fifth step, we say that consider the satellite now, the satellite in its orbit. So consider the satellites are now its orbit, means that outside the S's surface. So you say outside of the S's surface, the weight of the satellite, which is mass of the satellite times acceleration gravity dash on the satellites, okay, on the satellite surface, this should be balancing with the force of attractions between the satellite and the S times universal gravitational constant, and then here we have radius of the S plus the height h, and this is the square. So if that's the case, you say that the mass of the satellite times G dash, this is equal to the mass of the satellite, mass of the OT, mass of the S, universal gravitational constant, then radius of the S plus the height h square. So mass of the satellite cancel. So acceleration gravity on the satellite surface is equal to mass of the S times gravitational constant or universal gravitational constant times radius of the S, and then the height is square. So this is the third equation, right? So you have this is gravitation. This will give us acceleration gravity on the S's surface, and this equation will give us acceleration gravity on the satellite surface. So what I've been asked to find G dash. So then we go forward for the sixth step of the first step. So the sixth step, we say that now we have to take equation 3, we divide with equation 2. Why do we have to divide? Because we have to cancel. There is similarity between equation 2 and equation 1. Equation 2 and equation 3. So if we do division, then the numerators of both expressions, both equations will cancel. So you say G dash over G, this is equal to what? This is equal to the mass of the S times universal gravitational constant, and then times radius of the S plus the height h. This is G dash, but this should be squared. Then we multiply with your radius of the S square divided by mass of the S G, because you have to know that the basic operations of division will be replaced by the multiplications and then changing the positions of numerator and denominator. So we change the positions of his denominator becoming numerator, and the positions of this numerator becoming denominator. So if that's the case that these are the similar constants, so they will cancel, and then we say that G dash is equal to G, and then we have what? Radius of the S over radius of the S plus the height of the satellites above the S's surface square. Right? So you see that now we can do our computation by using the constant of given. This G is 9.8 meter per second square, and then you have to multiply with 60.5 exponent 6 meter divided by 6.5 exponent 6 meter plus 500 exponent 3 meter, and then square. So acceleration gravity is equal to it. So remember that meter and this meter will cancel, So it means that we remain with what? 9.8 meter per second square. And then we multiply by what? 6.5.